So, I introduce you to this topic. Before I go into this topic, on a request, I've published the project format. For I think one of the one undertaken by my former student. Okay, so those project that I publish, of course, they have on almost 100%. So if you really want to know, you want to have a sense of how the guideline or whatever is going to be so you can benefit from that. We started on Monday, what I call, uh, you know, binary logistic regression. I remember I walk you through, we differentiated between the general linear model and the generalized linear model. Because logistic regression, the variants of logistic regression, they actually fall under generalized linear model. And I remember I walk you through what is the role of a link function, and of course, what is the role of exponential family of distribution. And of course, I will briefly mention that again today before I move into the binary logistical regression. Now, when you take a look at what I'm displaying right now, of course, we derive this link function from the exponential family of distribution. We actually believe that the probability distribution of the response variable here follow an exponential family. And of course, we took advantage of that and we derived the link function, as you can see, or the link function for normal. You can see that the link function for binomial, you can see that, and the link function for Poisson, you can also see that. Okay, the one for Poisson is a log lambda, and the one for binomial is with the one we call logit, that we call the log of odd ratio, and of course the one for normal is identity. Now there's something I need you to pay attention. What is the role of the link function in a generalized linear model? I'm going to say that again. What is the role of link function, okay, in a generalized linear model? The number one point that I wanted to, uh, you know, to actually put into consideration is that it ensures predicted mean is in the right range. We don't want a situation whereby the predicted mean will be out of the range. For instance, if I'm talking about classification problem, we expect prediction to be between 0 and 1. With a situation where we don't apply a link function, we may not be able to guarantee that, and that's going to lead us into nonsensical prediction. We don't want a situation whereby, because it's a probability value, we don't want a negative, we don't want something greater than 1. So the link function, we ensure we guarantee that. Now, let me tell you this. You're actually going to guarantee positivity. You're going to guarantee non-negativity for the probability of the response variable in a classification problem. And not only that, actually going to restrict there's going to be a boundary, you're going to ensure that the range of the response is actually within 0, 1. Okay, so that is number one. And let me tell you this. If I actually want to capture correctly how predictor variables influence the response, of course, the link function is actually going to reveal that. Okay, the link function, when you change the link function, then you have changed relationship. So what we need to do here is if we want to build a model, for a particular relationship, we need to identify an appropriate link function. Okay, so like I said, the link function is very, very crucial. And let me also tell you this. When you use a different link function, you have different interpretation. Of course, the interpretation is going to change when the relationship change. Okay, and that's why you need to be very, very careful about the link function. Let me now tell you this. When I'm talking about, let me make use of my pointer. 1 second. When I'm talking about this guy, okay, the for normal linear regression, where the response variable is continuous, the link function is identity, okay, and what the identity is actually, talking about is that the coefficients are additive. I'm going to say that again. What identity is talking about is that the coefficient, that's a coefficient I'm actually referring to. Linear regression coefficient is additive. That is what it's talking about. Now, if you take a look at this one, for the binomial logistic regression, or where you have a leaf function to be logit, that we call the log of odd. Now, what that is trying to tell us is that the coefficients are odd ratio. Okay, we have the coefficient that are in odd ratio form. And lastly, when you take a look at the Poisson regression, or where the leaf function is log lambda, then that's actually telling you the coefficients are multiplicative. They are multiplicative. That's why we need a log. Does that make sense? Okay, so the moment you change the link function, okay, you are actually changing how predator affects the response. Okay, now I want to move. And the last thing I'm going to talk about the shape, the type of link function you use will determine the shape of the relationship. When you use the identity, it's going to tell, oh, I got a straight line relationship. But when we use a logit, okay, where the response variable is categorical, we shouldn't expect a straight line. When you have a straight line, you know what is going to happen? When you use a linear regression for a classification problem, you actually going to have your prediction is going to go out of the boundary of 0, 1. You're actually going to have nonsensical prediction. So therefore, we should be expecting a curve. Does that make sense? A curve. If you want to restrict, we should be expecting a curve. Okay, so and the shape of that of the Poisson regression, where you use a leaf function, we expect an exponential rate. Okay, another thing I want to talk about. I think I just gave you the role of the leaf function in a generalized linear model. But what is the role of exponential family? I want to talk about the role of exponential family of distribution, because for you to be able to use this approach, okay, the underlying probability distribution of the outcome variable must come from exponential family. When I talk about exponential family, what are the distribution am I talking about? I'm talking about Bernoulli. I'm talking about binomial. I'm talking about norma itself. I'm talking about exponential. I'm talking about Poisson distribution. I'm talking about gamma distributions. All of that actually fall in the exponential family. Now, why do we need the distribution of the response to follow exponential family? And that's what I want to discuss right now. I'm actually dishing out very valuable information that you need. We don't just do what we do. We got a reason why we do what we do. Now, I think I've already highlighted the role of link function in a generalized linear model. What I want to talk about now, actually, also want to give you what are the roles of the exponential family in a generalized linear model. Let me tell you this. If I actually want to know a proper relationship between the mean and the variance, then I need to use exponential family. Because we normally have issue when if you look at the linear regression, assumption is that the mean does not, the variance of the response does not depend on the mean. It does not depend on any predator. You understand what I mean by constant variance? If I want to have a proper relationship between how mean respond to variance or how variance respond to mean, then we need exponential family. So the proper relationship between the mean and variance can actually be guaranteed with the exponential family. Now, let me also tell you this. When a model is classified under generalized linear model, the method of estimation is usually method of maximum likelihood. I'm going to say that again. In the general linear model, where you have regression analysis, where you have analysis of variance, where you have all of that, we normally make use of least square approach. But when you're talking about generalized linear model, where the response variable is no longer continuous, where the response variable may be categorical, or the response variable may be a count, or the response variable may be a rate, then the method of estimating regression parameter is by method of maximum likelihood. Okay, I just wanted to take note of that. Let me tell you this. If the distribution of your response variable is from the exponential family, that method will work great. I'm going to say that again. The method of maximum likelihood work greatly when when the underlying distribution of the outcome variable is from exponential family. If it is not from exponential family, then you're going to have issue with the method of maximum likelihood estimation. You're going to have issue with stability. You're going to have issue when you are performing iterative procedure. You're actually going to have issue with the convergence rates. Okay, I think I just mentioned that. Now, you've listened to the story. We now want to go into logistic regression now. Now, let me tell you this. Why is it that I cannot use a linear regression for situation where the response variable is categorical? We've tried this before. There's before we can discover a way, maybe at times we need to first identify where there is no way. So when we identify where there's no way, then we're going to say, oh, that's a way. So we've tried using linear regression for classification problem. We realize this problem. Number one, there's going to be violation of assumption of constant variance. That's number one. Number two, there's going to be violations of linearity. Of course, you're never going to have a linear in a situation or where the response variable is categorical, and you're going to have a nonsensical prediction. Okay, and that's why we cannot use linear relationship for classification problem. And what we're going to use is to be able to generate a link function using the idea of exponential distribution. And of course, we believe the link function we can relate well, okay, linearly or to the predator. Now, let's come back to the logistic regression now. Okay, when you have a binary logistic, you are trying to say, okay, yes or no. Maybe your response variable is yes or no. What determine yes or no, or whether a particular customer that approach a bank is going to default or not, and the bank want to consider giving the person loan, and the bank is going to put into consideration some factors. Okay, that's binary response. Of course, we're going to use logistic regression here. Okay, if you can see an example here, a smoker, and you say that somebody smoke or not, or say that somebody survive or not. And of course, we also have what we call the ordinal responses. This is not, we can't use binomial logistic here. Okay, what we're going to use in this situation is going to be ordinal. Okay, we're going to talk about other form of logistic regression, and that is, I classify them as a variant of logistic regression, and that will be done on Friday. I want us to go into the model now, and I need you to pay attention. What I'm actually going to spend my time on, I'm going to spend my time on two type of logistic regression. the binary, the simple binary logistic and the multiple binary logistic. Okay. Now, what do I mean by simple binary logistic regression? Okay. The simple there means I have one predictor and I have one categorical response. So what make it simple is I got one predictor. And of course, today I'm also going to talk about, the multiple binary logistic regression. Look at the two. Simple binary logistic regression, multiple binary logistic regression. The binary appear in both sides means my response variable is categorical. The simple and the simple implied I got one predictor, the multiple implied I got multiple predictor. Now I needed to pay attention. This is the model. This is the logit. This module is in logit form. Now I'm talking about simple binary logistic regression because I only have a single predictor here. Now this is in a logit form, and of course the logit form here is actually coming from, that's a link function that we derive from the exponential family. Okay, now and the underlying probability distribution for the response from which this was derived is binomial distribution. Okay. Now, if I solve for pi, I'm actually going to have it in a probability form. So in the final, if I ask you to generate, maybe I give you output from uh, maybe R, and that's centered on logistic regression, and I say, can you write a model in a logit form? This is how to write a model in a logit form. All what you need to do is just to supply me what is your intercept, what is your slope. And if I say, okay, I want to get, can you get that in a probability form? This is in probability form. Does that make sense? Okay, now the pi here, maybe is the probability of yes. 1 minus pi is the probability of no. And that is why this is the odd ratio. Okay, now I'm moving. How do we do that now? Okay. Now, maybe I have I want to fit a logistic regression model, or I have a height as a predictor, and of course the response is gender. Okay. Now, when I want to fit a logistic regression model, I need to write a GLM. When I write a GLM, I have to indicate family equal binomial. If you don't indicate a family equal to binomial, the output that you're going to get will be linear regression outputs, even if you put a GLM. The GLM here means, you know what GLM means? The generalized linear model. Even if you put a GLM and you don't indicate family equal to binomial, the result is just going to be linear regression, and that will be wrong. Does that make sense? You have to put a family equal binomial. When I put it, so, oh my God, this is the summary. This is the result that we have right now, and I need you to pay attention to this. Take a look at this. Do you know that in the linear regression, we normally call this guy estimates, but in a logistic regression, we don't call them estimate. You know what we call them? Log odd estimates. Log odd. Why log odd? Because that is the logit. That is the link function. So the log odd or estimate, like if I want to talk about the log odd estimate for intercept is 64.1461. I'm not going to say estimate. I'm going to say log odd estimate. And if I want to interpret, I'm actually going to emphasize on the log odd. Okay. Now the log odd slope is that. Okay. I needed to pay attention. Now, now, if I have that, how do I write that in a logit form? How do I write that in a probability form? Okay, now the result here now is in a probability form. That's a pi curve. You know what a pi curve means? Because when I was doing this in R, okay, the pi actually represents the proportion of females. Okay, it represents the proportion of females. Okay, now the pi cap. Now it means if I'm giving, maybe I got some student, I have information about the height, but I can't see them. I don't know whether whether they are male or female. Okay, I want to use information about height to predict whether what I'm talking about is male or female. I'm going to use this model here. If I have information about height, I can predict the probability that the person is going to be a female. Does that make sense? In a bank, if that very pie represents the probability that a customer is going to default, maybe yes, maybe what is going to serve as a predictor, or maybe the credit history. Does that make sense? Then we can now, if I know the credit history of individual seeking for loan, I can use this to compute the probability that the person is going to default. Now, we want, in logistic regression, we normally want to provide interpretation to odd ratio. Let me tell you this. We normally want to provide interpretation to three things. Number one, log odd ratio, log odd. Another one is odd ratio. Okay. Another one is the probability. Okay. Those are the three things that we want to provide, interpretation about. Of course, that is odd ratio. I can have odd ratio without a log, where I'm looking into the ratio of yes to no. That's what we call odd ratio. It's similar to when a bank is looking into what is the ratio of a customer paying back, divided by a customer not paying back, which is going to be, that's the odd of yes. Now, from the odd, I can determine the pi. I can determine the probability. So this is just a mathematical way. If I have odd, all this in terms of probability, I can perform algebraic, or I can solve for pi and get pi in terms of odd. That's what this guy is talking about. Okay, like I said, this is a binary logistic regression in a logit form. Okay, and of course, uh, and this is the odd. We have a log odd, we have the odd. Okay, we can, and let me tell you this. Please pay attention. Here, give me 1 second. Here we believe that the log of odd is linearly related to the predictor. That is one of the assumptions in the logistic regression. Even though we know the response variable is not linearly related to predictor, but what is linearly related to predictor, it should be the logit. And here, so that is what I mean. That's what I said here. Logistic model assume a linear relationship between predictor and the log odd. It does not have a linear relationship between predictor and the response variable. No, the response variable is categorical. Does that make sense? Okay. Now, what happened? How do we interpret the slope in logistic regression? Don't forget, what the slope talk about is for every unit increase in a predictor, we actually want to see how the probability is actually going to move, or how the log odd is actually going to move. And that was why I said, okay, if I replace x by x plus 1, what is going to happen? Okay, now when I replace, initially, now odd equal to that. Can somebody tell me? If you take a look at that, how is my odd equal to that? Because if you take a look at this, please pay attention. Okay, if the log odd equal to that, then odd will be equal to the exponentiation. Does that make sense? Okay, if the log of odd equal to that, what is odd? Odd is going to be, you take the exponential of both sides. So odd is going to be exponentiation of that. Can you see that now? Now, if the odd is the exponentiation of that, okay, now take a look at what I'm doing now. Okay, this is a situation I'm talking about odd for x, but what if in a situation where there's an increase in 1 unit, for that, how that is going to be the odd, and if that is going to be the odd, I can look at the ratio of the two. Oh my God, I'm looking at the ratio here. When I finally simplify, then I'm going to have exponential raised to power beta 1. So which means if I want to provide an interpretation to slope in logistic regression, then I don't just need beta 1, but I need the exponentiation of beta 1. Does that make sense? That is what I'm going to provide interpretation for. If I want to provide interpretation for odd ratio, that is exactly what I'm going to do. But you know what? I'm still going to walk you through all of that. Now, We have a way that we normally assess a model. Of course, how do we assess logistic regression model? How do we know the model is actually doing a great job? How do we do the same under the linear regression model? And you know what is important? Okay, what is important is beta one. That beta one is very important. If I want to test hypothesis now, take a look at this. Okay, I want to test if beta one equal to zero or if it is not equal to zero. That's something I needed to pay attention to. Under linear regression, okay, this guy is not a Z. That guy was a T. We conduct a T test. Let me quickly show you something. Let me show you the outputs. There's something you're gonna see in the outputs, okay, okay, that you're not gonna see in the output of linear regression. Hmm, you're gonna see something now, okay. Take a look at this guy. What do you see? Z value. What do you see? P of Z. But in the case of linear regression, it was a T value. It was P of T. Can you see the difference now? Okay. Now, 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 if you take a look at what we have right now here, okay, we're looking at the effect of GPA, okay, maybe on the performance of a student. Maybe it said us, of course, and the performance is categorical, whether the student, and we can categorize that into two to use binary, whether the student is going to maybe pass or fail. Okay. Now we have this as a outpost that we generated, and we want to test this hypothesis. Okay. Now in testing this hypothesis, we're going to make use of this Z value, not T test. We're going to conduct a Z test. Okay. Of course, the Z test and the T test, they have the same formula. Okay. So it's going to be this guy. Give me 1 second. I'm going to clean up. Okay. Uh, it's going to be this guy. It's going to be this guy divided by this guy because we're saying that's divided by that. And what do we get? That will give you the Z value. This is the P value. Okay, please pay attention. That is the P value of the test. Now, what is the odd ratio? This is the odd ratio. You know what happened here? You know how I got the odd ratio? I want to award an extra credit now. I want to award an extra credit now. Can somebody tell me how do we get 1.73 for extra credit? How do we get that 1.73? Because they call that odd ratio. How do we get that? Can somebody tell me? How do we get 1.73? Okay, I'm gonna show you. It's right here. Hmm. This guy, that's what you're gonna use. Can you use your calculator now? What is exponential raised to power beta 1? Where's the beta 1? Hmm. This is the beta 1. What is the exponentiation of this? Confirm that. Exponential raised to power 0.545417. What do you have? What do you have? I want somebody to confirm this. Huh? You know what? You know what you can do? Exponential raised to power 0.545417. What do you have? Exactly, which is 1.73. This is the odd ratio. Does that make sense? But how has automatically compute that for you? What if I give you something like this in exam? Now you know the odd ratio is exponential raised to power beta 1. Now, right now, this is the odd ratio, and this is the confidence interval. You know why? This guy here, it's like a point. That's a point estimate. A point estimate could be wrong or right. Don't forget that. The point estimate could be wrong on that. All right. But this is the interval estimate. Take a look at that. You know what I want to do now? Let's look at the p-value here. Oh, sorry. Let's look at the p-value here. It's showing that at 0.05, we're rejecting the null hypothesis, right? You take a look at that. Rejecting the null hypothesis. And let me tell you, if you are rejecting the null hypothesis, okay, now if you take a look at this, Let's see what happened here. Let's see whether we can use a confidence interval to judge. Please pay attention. You considering the ratio between yes and no, having a disease or not. Okay. Now, if they are equal, if this is equal, we expect odd ratio to be what? To be 1. Does that make sense? If odd ratio equal to 1, then we are more likely not to reject this guy. But now, the odd ratio, if you take a look at this guy, it's 1.73. If I want to know, please pay attention. If I want to know whether the odd ratio is statistically significant, I'm going to say that again. If I want to know if odd ratio is statistically significant, you know what I'm going to see in the interval? The interval must not contain 1. I'm going to say that again. Maybe I want to test. Maybe I give you confidence interval for odd ratio. When the confidence interval for odd ratio include 1, then you are not rejecting H0. But when it include 1, okay, do we have 1 in that interval? No, there's no 1. 1 point, that's from 1.27 to 2.35. There's no 1. Because of that, the confidence interval is saying reject H0. The confidence interval agree with the p-value. Can you see that? The confidence interval and the p-value, they're doing the same thing. They performing the same role. Okay? Rejecting with the p-value when p-value is less than 0.05. Rejecting with confidence interval when the confidence interval does not include 1. That's what I mean. Okay. I'm moving. Take a look at this. Okay, so which is what I'm doing. Okay, this is the test. That's what I'm doing. Now, let me tell you this. What is the implication when you fail to reject H0 when the odd ratio is not statistically significant? It's not statistical. It's not the difference is not significantly different from 1. Then you know what you're trying to say? In actual sense, you're saying the log of odd does not depend on the predator. You're saying your log of odd is the intercept. You remember when we're working with linear regression, the simplest model in linear regression is the intercept model. So the simplest model in the logistic regression is that guy. When the log of odd is equal to beta naught. But situation where in the alternative, you know what that guy's saying? Alternative is saying, I need predator. Is there any question here? Okay. Now, this is the formula that we use to get the confidence interval. Okay, this is the formula. Can you see that? That's what we use to get the confidence interval. I only need to know the standard error. The standard error is going to be given. Then I need to know that, and this guy is going to be the table value. Okay, so that is the formula. Now, I want to move right now. I want to move into another situation. What if in a situation where the response variable is categorical? Predator is also categorical. Because the one we've been talking about here is when the predator is continuous. But what if in a situation where they are both categorical? Then I'm going to call that analysis of categorical variables. Now, analysis of categorical variables is also under logistic regression. Okay, take a look at this. This is an example. Okay, TMS for migraines. Okay, where I actually want to consider, taking a treatment against not taking a treatment. Not taking a treatment is when you are giving placebo. Has anybody heard about placebo? Placebo? Okay, in clinical trial, when they give you placebo, okay, placebo is nothing. They just want to compare the treatment with nothing. Okay, now please pay attention. How does if I'm going to do analysis of categorical variable, how will my data look like? Your data is going to come in form of a table. Take a look at this. Where you have this guy, that will be the predator. The predator is categorical. It's either you are giving a treatment or you're giving a placebo, and the response is also categorical. It's either you now have a pain-free or you do not have a pain-free. Does that make sense? So this is they have conducted a clinical trial here, and they make use of they gave 100 people the treatment, and they gave another 100 nothing, the placebo, and out of the 100 that were given the TMS, okay, the pain free 39 as a pain free, okay, and for the placebo 22 as a pain free. Let me tell you something. If you want to know the potency of a new drug, we normally compare with nothing. Nothing is placebo. And let me tell you this: when some people get sick, even at time that depends on antibody. When some people get sick, okay, if they don't even take any treatment, they may be fine. Look at that, 22 get fine. Look at that, 22 actually get fine out of 100, but 39 get fine out of 100 when they have the treatment. If you take a look at this, now the question now, how do we actually know whether the treatment work? Then we're going to perform analysis of categorical variable. Okay, now in the analysis, I need a pie curve. Take a look at that. The pie curve, okay, is actually going to be 39 divided by 100. That is a probability that of actually recording it pain-free when you use the treatment. Please pay attention. Now, I also, I got this guy. I also need to get this guy. Don't forget, I'm going to do a hard. Hard is going to be, oh, after using the treatment, what is the number of people that record pain-free? Okay, and how many did not record pain free? That's what you have here. And of course, I'm actually going to do the ratio of that. That's actually going to give me 0.639. Please pay attention. Okay, when I get that, hmm, take a look at that. When my heart equal to that, then I can get my pi out. Okay, and my pi is 6.39. Look at that. It's 6.39. Now, when I get a pi out, what is the implication? I'm going to get pi out 42. Hmm. I get a pi out. This is for those ones that record pain-free with a treatment and the one that record pain-free with a placebo. Take a look at that. And after that, I will also do the odd ratio for the placebo. Take a look at this. The odd ratio for the placebo. I do the odd ratio for the TMS. And at the end of the day, oh my God, I'm actually going to do a general odd ratio. Odd ratio for placebo, odd ratio for the treatment, and I'm getting 2.27 now. Okay, let me tell you this. If the odd ratio between treatment and the placebo is 1, then why am I wasting resources? Okay, the treatment and the placebo are equally effective. Then I don't need to waste my money using treatment. Does that make sense? But when the ratio is greater than 1 or is less than 1, then 1 is good. 1 is better. Now I got 2.27 now. It now depends on what I put at the top. Hmm. This is actually coming. 0.62639 is actually the hard for the TMS is the one I put on the top. Now, when I put something at the top and the ratio is greater than 1, then what I put on the top is bigger, right? Okay. Now, what does that mean? Oh my God. That is the interpretation. It means the odds are 2.27 times higher of getting relief using the TMS than the placebo. That is the odd of getting relief. That is what that guy means. Okay. Now, if I don't want to go manually, the way I've gone manually to compute this, if I want to make use of software, how is it going to be? That's it. How do we do analysis of categorical variables in R? Because all what I've been doing here, I just go manually, right? If I want to use that, oh my God, look at what I'm going to do. This is the code. And I'm actually going to use a chi-square. We use a chi-square test in analysis of categorical variables. And right now, let's see what is going on. Let's take, you're actually saying p-value, right? Okay. The p-value that you're trying to see here is actually saying the treatment work. Now, I need you to pay attention. Let's see the result in general. This is the result now. This is the, take a look at that. Please pay attention. If you take a look at what I actually have now, okay, the TMS now, okay, the p-value, this is the p-value associated with that. I need you to pay attention to something. I'm seeing something now. Let me come here. I'm gonna show you something now. What we compute manually here, okay, yeah, we got 2.27. Hmm, that 2.27 is exponential raised to power beta 1. So if you come here, can you try this? What is the exponential raised to power that? Can you use calculator? It's actually that. I told you. Because the arrow output will not give you the odd estimate directly. If you want to find the odd estimate, you're going to do exponential raised to power the estimate, the slope estimate. And I give you 2.27. That we compute manually the other time. Can you see that? That's super cool. Okay, now, is there any question here? Or before going into the next material? Is there any question? Okay, I'm going to stop my share. This is being recorded. I'm going to stop my share. 1 second. And I'm going to quickly walk you through the other material. Okay, yep. So if you don't finish that, we're gonna continue from where we stop. Okay, I'm gonna show you this now. Come on, come on, come on, come on. Where you? Now, take a look at that. I want to welcome you to multiple logistic regression. Why is it multiple? Because the numbers of predator is more than one. But the response variable is the categorical. Now, I'm going to walk you through the introduction to that. That is similar to multiple linear regression. We use likelihood ratio test and how the way, what are the steps involved in the analysis of that. This is the model. We haven't extended, right? Because the number of predator has increased. Now, do you know what I'm showing now? I'm actually showing you in logit form and in probability form. This is in logit form. This is in probability form. Can you see that? Now we consider a situation now where the numbers of predator is more than one. This is multiple binary logistic regression. Okay, maybe the bank want to consider, um, you know, a loan. A customer apply for loan, and they want to put into consideration so many predator, the credit history, the balance, whether this person is a student or not, and so on like that. So that's what we mean here. Now, pay attention. You remember when we're dealing with a simple binary logistic, we compare intercept model with a model, right? With a model with covariates. Now here, if you take a look at this, if I'm comparing, here I'm trying to say in the H naught, all the slope is zero except the intercept. It's like I'm comparing intercept with a model with covariates. And let me tell you this. What is a test statistic? You remember the other time when I was talking about simple binary logistic, the test statistic was a z-test, but it is no longer a z-test now. Okay, the statistic is G. The test statistic is going to be G, where we're actually going to have a log likelihood. We're going to have a log likelihood assuming H naught is true, then the log likelihood as assuming the alternative is true, then we multiply by -2. But you know what? So another way to say this is having a reduced model against a full model. Okay, can have a reduced model against a full model. And when I say reduced model against a full model, we can have a situation where no predator at all. against the model with covariate, or we can also have situation where we have a fewer numbers of predictor against a full model. We did that under linear regression. We're also going to do the same here. I quickly want to walk you through this example, but if you want to have access to that, you need to load a library called LM test. Now, this is the data. This very data, you can have access to that if you copy that into R. This is online data. Okay, where we actually want to identify some predictor that determine whether a student is going to pass a class or not. We consider age, travel time, study time, absences. Okay, the midterm 1 grade, the midterm 2 grade, and the final grade, of course. So we actually all of that have connection to a student passing a class. Now, because of that, we actually want to compare between using a simple model and a complicated model. We did that in linear regression when we're dealing with nested models. We did that in linear and non-linear models. We're also going to do the same here. We're actually going to call that a likelihood ratio test. Let's see how we do it. Simple model. Let's look at a simple model. In the simple model, what this guy is trying to say, oh, it's only absences that determine final grade. Okay. But in the complicated model, he said, no, 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 it's not only absences. Okay. Age as well. Then how do we know which one is a better one? Then we're going to, instead of us to say ANOVA test, you remember, we want to say ANOVA into that. We don't do that here. We're going to say LR test. Okay. When I do that, we're gonna run it, and this is the p-value. Okay, we compare the p-value with the level of significance. Okay, here the p-value is less than 0.05. We're going to reject a simpler model for complicated model. Decision remain the same. That makes sense? Okay, so if I want to compare here now, I want to compare a model that have a study time and midterm 1 score with a complicated model. Okay, with a complicated model. Give me 1 second. With a complicated model, that's that. The p-value. Can you see that? It's the same way. Okay. Now, uh, what are the steps involved in analysis of logistic regression model? I want us to visit bank. Somebody apply for a loan, and the bank want to decide. Okay, but the bank has information about 10,000 customers. They have this is a supervised learning. They have information about some people have borrowed money in the bank before, some default, some did not default. They have that information. Does that make sense? Now, they have information on whether the person is a student or not. They have information about the balance on the account. They have information about the income of individual, and of course, you know what? I don't want to rush you. Practically, I want to walk you through how the bank can actually use multiple logistic regression to decide on this classification problem, because this particular bank want to classify new customer that has applied for loan, but they have available information like about 10,000 customers. Some of them are, they borrowed money in the bank before, some of them defaulted, some of them did not. Okay. And how do what is the procedure, to go over that? Okay. You can look at that before we leave, we meet next time. Okay. I'm actually going to talk about the process, the assumptions and so on like that. I'm going to walk you through that on Friday. Is there any question for me before I go today? This is where I'm actually going to stop. Tomorrow, I'm going to post the exam too, but there's nothing to worry about because you guys had impressive performance. And that's why I'm happy. You're going to see that tomorrow. So bye for now, everyone.